Let us now proceed and demonstrate the idea of working with notched members through an example. And the last piece of information that we need for this purpose is the possible or possibly different value of KFM with respect to KF. And indeed, the convention dictates that KFM, in other words, the fatigue notch factor for the mean stress, mean nominal stress, is equal to Kf if one works with brittle materials. On the other hand, when one works with ductile materials, the convention or the argument is that one can remove the influence of stress concentration altogether. In other words, take the fatigue notch factor to be 1 for the mean stress only. The value on the alternating stress remains the same. And the argument here is that the stress concentration would lead to stresses that are so high which would essentially not be tolerated by the material, and the material would yield and remove the influence of the stress concentration, provided that it's ductile. If it's brittle, say it's going to locally crack, and that influence of the concentration will be reflected fully through the fatigue notch factor. But if it's ductile, it can yield and therefore remove that effect significantly. So for ductile materials, we're going to take the KFM value to be 1. Okay, with that understanding of our basic strategy, now we can go ahead and proceed with an example. And the example is going to be based on a notched plate. Let me first depict the setup. So we have a plate which has a transition to a thinner region on the two outer edges. So that's the geometry we're dealing with. Okay, and we are given what the thickness is, as well as the width of the plate in the thinner and the thicker portions. And the plate is loaded through a pure bending moment. That's going to be cycled in some fashion. And moreover, we have a notch radius here, which is rho. Okay. So the material is given as RQC 100 steel, which is noted to be a ductile material. All right. So the question is, well, we are given the geometric parameters, which I will summarize in a second, but eventually what we desire is that we should be able to apply 1,000,000 cycles with a mean value of the bending moment at 4 kilonewton meters, and what we're trying to figure out is the maximum value of the alternating portion of the bending moment such that we ensure this many cycles. Here the safety factor is not given, so we can say that in this case within a safety factor of 1. Alright, so the geometrical parameters are as follows. The notch radius is 4 millimeters, W1 is 80 millimeters, W2 is 88 millimeters, and finally the thickness is 10 millimeters. Now, for a given value of the bending moments, we also remember in the scenario that the nominal stress is calculated, it's associated with the maximum stress at the smaller cross-section in the vicinity of the notch. So we're going to calculate essentially MC over I. We're going to apply that equation with C corresponding to the smaller portion, W1 over 2, and therefore I being equal to 1 over 12 W1 cube on T. So the value of S is 6M over W1 squared T. So now we're trying to find the maximum value of the alternating bending moment. Let's think about our solution scheme. That's our first step, because if we can visualize the solution scheme, then the rest is going to be easier. So we should fully always understand why we're doing and for what purpose, and the details are second, because we can always refer to our reference books on the details. But the general strategy should be clear in our minds, even for a seemingly complicated scenario, as in the case of fatigue of Nash members. So first of all, I see that there is both an alternating and a mean component to the bending moment. So suppose we knew both of these. Presently we are actually given only the mean part, but suppose we knew both of them. Then what I could do is I could calculate through our equation the nominal stress associated with each part. Now, it's not a pure reverse or complete reverse alternating stress, so I know that I have to take these and map them to a equivalent completely reversed nominal stress, and that's going to be a function of SA and SM. But that's not what we apply in the Basquin equation. In the Basquin equation, I need the point stress, which is associated with life through the classical Basquin form. And the point stress is a factor times the nominal completely reverse stress amplitude. But that factor is not the elastic stress concentration factor, but it's actually the fatigue notch factor. So we need an additional map here where we take the actual elastic stress concentration factor, additionally calculate a notch sensitivity Q, and then using these I need to calculate KF and then proceed with the rest of the map. Okay, so starting here I end up there. Now presently the problem is set up in exactly the reverse manner. We're given the life, and so that's 10 to the 6, and therefore I can determine sigma AR. From the geometry of the problem and by finding the value of Q, I actually can determine what KF is. So given this and KF, I can determine SAR, the equivalent completely reversed nominal stress amplitude. So I know SAR, and it's a given function of SA and SM. In the present case, remember that we're going to prefer using either modified Goodman or the, let's say, SWT equation. But I know this equation. And presently, I also know the mean bending moment, and therefore I know SM. So SAR and SM are given. I'm going to solve for SA and work backwards towards MA. So I'm going to start here and end up with this unknown value in the upper branch. Okay, so that's the idea. So let's proceed with this strategy. So we're going to work backwards. Okay, so step number 1. We're given the life. So why don't we find, therefore, the equivalent completely reverse point stress amplitude, sigma AR, which is sigma F prime 2 NF to the power B. So presently, we can either use that form or the alternative form A and F to the power B. Remember, B is the same as small b. In this case, by looking at the material property for RQC 100 steel, we can find that B is equal to minus 0.0648. And A is 897 MPa, and NF is given as 10 to the 6 cycles. So we can find sigma AR to be 366 MPa. So now I know that value. Okay, so we were given this. Now I also know sigma AR, and now if I determine KF, I can determine what SAR is. So my next goal is to determine the value of the fatigue notch factor. So the first step towards that is to determine the value of the stress concentration factor. So eventually you will recall that there are figures in which the stress concentration factor is going to be read. So for instance, for this particular case, it's going to be a function of rho over W, and we're going to read the value of the corresponding KT from figures that looks like this, and in which each line corresponds to a particular value of W2 over W1, and as the ratio increases, the situation becomes more critical because the transition in the geometry becomes more severe and KT value increases. So I need to go with the correct value of W2 over W1 and rho over W1, and this figure is provided in the appendix. So presently rho over W1 is equal to 4 millimeters over 80 millimeters, which is 0.05, and W2 over W1 is 88 millimeters over 80 millimeters, which is about 1.1. So we can go to the appendix figure in the book, which looks pretty much like that, and read the corresponding value for this given rho over W1 and W2 over W1 ratio. If it doesn't fall on any one of the given lines, you remember we have to somehow visually interpolate, and KT can be found to be about 1.85. So we know the value of KT, but that's not equal to KF. So I need to also determine the notch sensitivity. So the notch sensitivity, remember, is something that lies between 0 and 1. If KF is equal to KT, the value is 1. If KF is 1, the value is 0. So that's the way it is presented. So the question is, what is that value? Now presently, I have determined that KT is equal to 1.85. So if I determine Q, I know the value of KF. So we're going to use here Peterson model, which is good for steels. And the Peterson model, remember, says that Q is equal to, now this part one doesn't really have to memorize at all, or for that matter, it's hard to learn and make sense out of it, but that's the form where rho is the value of the notch radius, which is again 4 millimeters, and the alpha value is to be determined. So the alpha value is, again, in the Peterson model, there is an explicit expression for alpha as a function of sigma u, which we had written in an earlier slide. Presently, the material property is such that sigma u is 758 MPa. So if you take that and plug it into that logarithmic expression for alpha, you will find that the value of alpha is equal to, and remember the value is given as millimeters, 0.148 millimeters. So if you want here again, refer to earlier slide or the equation in the book. And eventually, so now that we know the value of alpha, we can go back and plug it in there, okay, and find that Q is equal to 0.964. Okay. So now that we know the value of Q and we know the value of KF, we can go up here and essentially determine the value of KF, which is determined to be 1.82. Right? That's equal to 0.964. And so given KT, I know that Q is its KF is equal to 1.82. So now Remember what we had done. Given the life, we determined sigma AR, and now I've determined also KF. So now I can go and find the value of SAR. So now I know what SAR is, right? So KF SAR is equal to sigma AR, and therefore SAR is equal to sigma AR over KF, which is equal to 201 MPa. Notice that the difference between KF and KT is not much, but in general it could have been. KF can be as small as 1, so it's important to stick to this overall procedure and be consistent with our discussion. So presently, that's the value of SAR that we have found out, 201 MPa. Now, where we are presently is, we are at this stage. We know the value of SAR, 201 MPa, and actually, remember, we were already from the outset given the mean bending moment, so we could have calculated SM. So, in fact, we know that from directly this equation, the value of SM is equal to, right, by substituting M equals 4 kilonewton meters, we know that SM is 375 MPa. So now SM is given and SAR is known, and if I have a function that relates SA and SM to SAR, there is only one unknown, SA, and I can solve for it. So the question is now, therefore, at this stage, what is SA? And for that, I need to pick a proposal for the form of the function. I will pick two proposals. The first proposal is the modified Goodman equation. And modified Goodman works as we already discussed, so I'm just going to write down the result that relates SAR to SA and SM. So it's SA over 1 minus KFM SM divided by, for modified Goodman, the critical value is sigma u. So sigma u is something we already know. It is 758 MPa. And actually we know that the material is ductile, and with that given information I will take KFM equals 1. So this here is equal to 1. Okay, so SM we already have calculated with the given information. It's 375 MPa, and now that we also know the value of SAR, which is 201 MPa, we can determine the value of SA, which is 102 MPa. Now, as soon as we know the value of SA, okay, I can go and from this equation find the corresponding value of the alternating component of the bending moment, in other words, MA. So once we have that equation, we can find that MA is equal to 1.09 kilonewton meters. All right, so that's the result with modified Goodman. Now what I'm going to do now is I'm going to work out the same thing with the second approach, which is the SWT approach. So let's write it from right to left. So SWT approach is going to say that, well, okay, so SAR is again a function of the mean and the alternating components of the nominal stress, but in this case that relation is through S max times SA. Okay, it's just still some function of SA and SM, and that's the form of the function for the Smith-Watson-Tupper approach. And here S max is equal to SM plus SA. So now there is no material parameter here, unlike the modified Goodman, and in fact KFM even does not appear in there. And we already know the value of SM. It is given. It is 375 MPa. We already calculated it. So, and we know the right-hand side, we've already calculated that as well, it's 201 MPa. So there is only one unknown, which is SA. Now notice that if I square both sides, I will have a quadratic equation for SA. You can solve for it easily. The meaningful root is 87.5 MPa. Okay, so similar to this case, what we've done is we've solved for SA, and once I know the value of the alternating nominal stress, then I can find the alternating bending moment through this equation, and that result is MA equals 0.933 kilonewton meters. So that is our strategy, and the strategy branches only in the choice of the function of SAR, and possibly, of course, you could have chosen a slightly different model that's going to give a result that's very similar to this as well, by not using the Peterson approach, but the Neuber model instead. But here we've made a choice between the two models for mapping alternating and mean to a completely reverse equivalent alternating nominal stress. And that choice, notice, although the functions look very, very different, they both ultimately predict that the maximum alternating bending moment you can apply in the presence of such a mean value is of the order of 1 kilonewton meters. So despite the fact that the models look very similar, you see engineering wise and to within probably a good safety factor which we did not have presently, they work just as fine. So you know that to a good reliability here, to the extent that we know that these models do work well, and to that extent we know that the maximum alternating bending moment we apply is 1 kilonewton meter. So again, I should highlight that the solution scheme should be clear in our minds, but of course for the details, for the figures, for the equations, etc., we always have to refer to references, but the solution scheme should be absolutely clear in our minds.